talking about PVNRT, and I'll be discussing what PVNRT is. So PVNRT is an ideal gas law, where the P stands for pressure, V stands for volume, N stands for the moles, stands for the constant, and T equals the temperature. So in PVNRT, the R is the universal gas constant, and it usually equals 0.08206 kilojoules per mole.
Some of the other gas constants we use, as said before, we normally use 0.08206 when the units are liters, atmosphere for pressure, moles, and Kelvin, but there are other constants that we use periodically for different units. We're doing a practice problem. So the problem says, what pressure is exerted by 0.325 moles of hydrogen gas in a 4.08 container at 35 degrees Celsius? So our first step is to write out the equation, PV equals nRT, and since we're solving for pressure, we have to divide by volume to get pressure by itself on the left side. So now we have P equals nRT divided by V. So now we just have to plug everything in. So P equals, the first we have moles, so 0.325 moles, times R, which is our constant. So for this one, we're going to be using 0.08206 for a constant, because all the units for 0.08206 are the same for the problem besides Celsius, which we're going to have to convert to Kelvin. So now we have Kelvin. So we just add 273 to 35 degrees Celsius, which gives us 308 Kelvin, divided all by 4.08 liters, which if you put this in your calculator, you get pressure equals 2.01 atm. And as you can see in the problem, the other units all cancel out. Moles, Kelvin, and liters, and you're left with ATM.
Okay guys, now we're going to be moving on to practice problem number 2. How many grams of oxygen gas are there in a 2.0 liter bottle under STP conditions? So first we're going to start off writing out our equation, which is PV equals nRT. And since we're going to be wanting to find the grams, we're going to start and solve for moles. So we're going to switch around the equation, and then we're going to do moles is equal to PV, yikes, PV over RT. And then, since it's STP conditions, we know that our temperature is equal to 0 degrees Celsius, and our pressure is equal to 1 atmosphere. Now, all we have to do is plug into the equation. So our pressure is going to be 1 atmosphere multiplied by 2.0 liters, which is the given, and all of that divided by the constant R, which is 0.08206, and this is going to be liters multiplied by atmospheres divided by moles times kilograms. Times Kelvin, sorry. And then that multiplied by the temperature, which is 0 degrees Celsius, but we're going to try and convert that to Kelvin. So in reality, it is 273 Kelvin. And now we're just going to solve for moles, and we get 0.0893 moles of oxygen gas. And now all we have to do is convert that to grams. So we have 0.0893 moles of oxygen. We're going to multiply that by grams of oxygen. And since it's diatomic, it's going to be 16 times 2, which is 32.00 grams of O2 divided by 1 mole. And we get 2.9 grams of oxygen gas. Thank you.
So now we're doing another problem, and this problem is a rigid 15 liter tank contains 20 moles of oxygen gas at 22 degrees Celsius. Calculate the pressure under ideal gas conditions. So we have PVNRT right here. And so then we divide by V on both sides. So then we get P equals nRT divided by V. So we have our pressure. We don't know that yet. So we're going to solve for that. Then we have the V, which equals 15 liters. N, which equals 20 moles. The R, which is the constant of 0.0206. And then T, which is the 22 degrees Celsius. But we're going to convert that into Kelvin. So we have 295 degrees Kelvin. And so then we're just going to plug that in. So P equals N, which is the moles. So 20.0 moles. R, which is our constant, 0.08206. And then we have the T, which is 295 degrees Kelvin. Not degrees Kelvin, just Kelvin. And then divide that by our V, which is 15 liters. And you should get 32.3 atmospheric pressures. Here we go.
This problem number 3. So today we have a collab between Jenna
and Rosy.
So first we're going to start by reading the problem.
An excess amount of magnesium is added to 0.0400 moles of hydrochloric acid at 0 degrees Celsius and 1 atm pressure. This is also known as standard temperature and pressure.
STP, yeah.
What volume in milliliters of H2 gas can be obtained?
So first, to do this problem, we have to start out by writing an equation. So as it said, we have magnesium, which is a solid. Make sure to always add your units. And then we have
add your state of matter.
Yeah, add your state of matter. Always make sure to add that. And then you have HCl, which is an aqueous. Make sure. And then
What? It's a cute.
It's a cute.
What is cute?
That is a cute. Okay. So and then the reaction is M magnesia, which is an aqueous. Magnesium chloride plus H2 gas. So now to balance this equation, we have to add in 2 in front of the HCl here. And
To balance that out with the H on the other side.
yeah, so 2 H's here because it has H2 over here.
And
then
we're
everything
done.
else is balanced there. So now we want to solve for volume. So the equation is going to be V equals nRT divided by P. And how we got that equation is we just feng shuied the equation around a little bit to get V instead of solving for a P instead of PVNRT. So Rosie will take over.
So now all we have to do is plug in the values. But first we have to solve for moles. So we're going to start off with 0.0400 moles of HCl, and we're going to multiply that by 1 mole of H2. Remember, hydrogen is diatomic. And we're going to divide that by 2 moles of HCl. And thus, by solving this equation, we get 0.0200 moles of H2. And now we can plug that into the equation solving for volume.
Okay. So we have volume equals our moles, which is 0.0200 moles of H2 multiplied by our constant, 0.08206, and multiplied by our temperature, and because it's STP, it's just 273 Kelvin, and then divided by pressure, which is 1 atm. And when you put that in your calculator, you get volume equals 448 milliliters of H2.
Thanks for listening.
Have a nice day.
Nice.
Oh, shoot.